Thank you. And let's welcome Professor Bing Yu. And Professor Bing Yu is a Chancellor's Distinguished Professor and the class of 1936 second chair at UC Berkeley. I haven't quite worked out the class of 1936 yet, but seems to be quite important
They
honor.
donated the money.
Okay, excellent. And Bing obtained her BS degrees in mathematics from Beijing University and her MS and a PhD degree in statistics from UC Berkeley. And she has been a faculty member and a visiting members at a large number of universities, from medicine, Yale and MIT, ETH, Bell Labs, and INRAIL, Peking, and New Things in Cambridge, and Toronto. Just so many of them, and she must be really, really a popular research and lecturer in a lot of places. And she's a member of National Academy of Sciences and of American Academy of Arts and Science, and the past president of the Institute of Mathematical Statistics, and had a good number of prizes and honors and so on. And one important thing she probably would like to talk to today is the PCS framework she developed for Veridical data science, and the PCS here stands for predictability and computability and stability. And without further ado, let's listen to Professor Bing Yu's talk on Veridical data science for trustworthy AI. It's yours.
Thank you. Thank you, Amos, for inviting me, and Ming, for the very kind introduction. So all the positions, they're mostly a visiting position. So it's not like I had so many different jobs. And it's a pleasure to be here. I don't think I have ever spoken in this workshop, so I look forward to having feedback from all of you. There's some construction going on. I hope you guys don't hear it. It's quite noisy where the house is. So hopefully it's not too bad. So as Ming said, I'm going to speak on this PCS framework, and also a case study where it's one of the most like 4 examples that we use to motivate the framework. In case you're wondering what's veridical data science, here's the definition. So veridical means truthful, coinciding with reality. If you speak Spanish, my Spanish friend tell me that actually still very much in use. For means like real, but in English, I think it's not as commonly used. So I think we kind of live in the age of AI, right? Many things got thrown under the banner of AI, and we can debate what does it mean, but it's a popular term that most people will associate with. They might not know what data science, but they feel like they know something about AI. I quite like this quote by Bill Gates from 2019, who said that AI is like nuclear energy, both promising and dangerous. So that's what I usually, for the last 10 years, live in a lot of the world of biomedical problems, and in particular, precision medicine and neuroscience, which you'll hear later. And data science is really a key element of AI, that under the hood of any AI system, there's some data-driven decisions made or recommendations. And machine learning is really like a power engine under the current version of AI. And machine learning sits at the interface of computer science and math stats, and also data science also include domain knowledge. So some people think data science is the intersect, some people think it's the union. Again, it's debatable, but we definitely, most of us recognize that it's really a multidiscipline area, and in terms of traditional disciplines. And it's really helping us to break down the barriers between different fields. I like to think data science as a system. So I think maybe many of you are engineers. I like to think as an entire process instead of like the modeling and the algorithm bit, which is the the circle down there. I work, we usually work with, say, domain scientists such as cardiologists or emergency room doctors. They have a specific problem they want to answer. For example, we're working under the BioHub grant with cardiology from Stanford and UCSF. We try to figure out a particular heart disease called HCM, hypertrophic myopathy, which is thickening of the left ventricle chamber that create heart problems. That can we find some genetic components of that and hopefully understand what will induce the condition. Of course, there are a lot of environmental factors as well. So that's kind of problem formulation. And then you look for data, right? We use UK Biobank data, but we're learning that the UK Biobank is very noisy because for older people, mostly white race, that it's not the best. And then there's always data cleaning. Well, that's something really put under the rug a lot. Data cleaning is a huge part of data science, and most of us who, the group do data analysis, you can easily spend 60 to 80% of your energy on data cleaning. And that's not recognized. And then we kind of move after data visualization to the modeling work, which is very much mathematical symbols. The symbols don't really help us to solve problems unless they have good correspondence with reality. And that's the part I think is very weak link in education and research culture. We just started with X and Y, which I did for many, many decades, that without the good connection with reality, all the math and all the code don't really help us to solve real problems. And then you have post-analysis, and many of these steps are not linear, right? When I do modeling, I realize my particular featureization or data cleaning was not kosher. So I go back, redo everything. It's very interactive, the different steps, but it's really a system. And there are different parts that can be taken out. We make so many human judgment calls. You ask 2 graduate students to clean the data. Actually, my first applied statistics lab in the PhD program, I have 36 students last semester. I'm sure I give them the same data cleaning problem. They're going to get 36 different versions of the same data. And do we get the same result? So this is a kind of we try to do. We really need a quality control and standardization so that we can maximize the promise and mitigate the dangers. So we define veridical data science as extracting reliable, reproducible information from data, and with an enriched technical language to communicate and evaluate empirical evidence in the context of human decision and domain knowledge. For example, deep learning, I was at the first talk this morning. It's introducing a pretty non-transparent, useful machinery to this data science enterprise. And we don't even have enough language to describe the different behaviors of this deep learning method. And that's what I mean by enriched technical language. How can we communicate and build on each other's wisdom? We need a technical language to say, hey, you ran this deep learning, and this is the phenomenon. Oh, that's similar in mine. Like, how do we describe and even communicate with each other? So for the rest of the talk, I will give you more details about what I mean by PCS framework. Kindly introduce what's the meaning of PCS: predictability, computability, and stability. And then the second one is a neuroscience case study to use the principles for neuroscience. And then I did the third bit. If I have time, I will introduce a pipeline my group developed for interpreting deep learning. So PCS framework for routine science. So 20 years ago, I think most of you here probably remember Harry Potter, right? That was quite a sensation, the book and later the movie. But what more relevant to this talk is really Leo Braman's paper, Statistical Modeling the Two Cultures. That was the time I got into machine learning. And Leo was a colleague in the department. He definitely encouraged me. He kind of got me to go to the first now called Neuroscience conference. And he called one culture algorithmic modeling culture, the other more traditional generative model, data modeling culture. It's not like generative models are not good. It's just when the generative model, the ingredients have no domain science support, you basically creating a probabilistic model that is kind of on shaky ground. And then we might just be honest and say, we just use that to get some algorithm going. So machine learning and statistics, I see machine learning as a modern statistic actually. They were always connected, right? And for a particular reason, this cross validation, which is a very important workhorse for machine learning, was invented by statistics in the 70s, but it's not essential for statistics. And what we try to do with TCS is really build a better bridge and integrate and streamline machine learning and statistics and expand on both. So the paper finally came out last year. It's a co-author with my former student and Kumbir, who is a postdoc at UCSF, and took 3 or 4 years. First, I was writing by myself, and then invited Carl to join me. It was the most difficult paper to write for me because things were evolving, my thinking was evolving, and was at the level that I was not used to. Usually, we do more technical work. So P means predictability. It's really taken from both machine learning and statistics, and computability. It's really like the engine power, both all data-driven work. And stability is really expansion on the inference of statistics, like sample-to-sample variability. We usually in statistics, we do confidence interval. We worry that, oh, I have this data, but I could have observed another set of the data under similar conditions, and therefore I want to control the variability. So generalizing that concept of whole data science pipeline, we can see sample-to-sample variability is really like a perturbation. And we have many, many other perturbations that we do, usually driven by human judgment calls, that we need to worry about the stability relative to that. I think data science is both an engineering field and a scientific field. And predictability and stability really embed 2 very important scientific principles: prediction and replication, right? In Popper scientific philosophy, we use prediction to falsify hypotheses, and replication is very much embedded in web science. You want another lab to replicate the same discovery. Computability in terms of computation and complex analysis optimization is very much part of machine learning, but computability under PCS also includes data-inspired simulations. I think we can gain a lot by having carefully designed simulated models and to understand the different methods, because we kind of know the truth there. I started to pursue stability kind of predictably very much. It was taken from machine learning. I mean, it was in statistics, but machine learning really made predictability pretty a central part of machine learning and current statistics or data science. I started working on stability as a general principle about 10 years ago. It was a 2-key lecture I was fortunate to give for Bernoulli Society. At the time, there was a lot of coverage of irreproducibility of the biological discoveries. So like we'll call the reproducibility crisis. And as I mentioned, right, sample-to-sample variability from classical statistics is a form of perturbation to the current data you have. And we recognize there are many, many, many other perturbations. So for example, if you have this L1 penalized squares, if you change the data by 10%, the variables selected often change quite a bit. That's what I was using for neuroscience problem. And Tukey was very much interested in model perturbation, right? He wanted to go after some like concept of the center of a data distribution that's robust against heavier tail, or you have outliers. So he was really thinking about stability related to the model perturbation. So put it together, I kind of put everything under stability, and also recognizing that classical statistical mathematical foundation centered in theorem is very much a stability result, right? Many of us know that there's another one way to prove centered in theorem is the Linderberg's swapping trick. You kind of have sequence of random variables, and you swap one by one the ones with the same mean, same second order, and then you can show that they're not that different. And if you swap everything by Gaussian, you basically have centered in theorem proved. So it's stability, concentration, all centered in theorem and concentration are all stability results. And stability is also a common sense principle that there are quotes by Plato, right? Many, many years ago, saying that knowledge has to be tied down, unlike opinion. Our opinion could change day to day, but knowledge shouldn't change today and tomorrow. At least there should be a much longer period that the knowledge will hold. Stability is really a minimum requirement for interpretability, right? You don't want things to change a lot and interpret that, and reproducibility, and also for scientific hypothesis generation or intervention design in causal inference. So this is this example to kind of ground what I'm talking about. This is a very well-known like a study or survey of workers, skills. They test literacy, numeracy, and problem solving. So actually there's an organization called OPAC. They sent interview to different countries, and then they gather, and that's how we evaluate the different skills of workers. And they, yes, are there questions? They sent interviews to the homes of these workers, and they sometimes take an audio, sometimes they take a video, and then the person will summarize the interview, right? So you can see that if you take an audio or video, you might get different impressions. So there are different ways the data generates already have many perturbations of human judgment calls, how you collect data, and then how you summarize, that's going to be different too, depending on who's the interviewer. So I'm just saying that before we should put a mathematical structure on it, we really need to understand where the data come from and the process and the perturbations and the human judgment calls. Otherwise, I don't think we're on solid ground. So PCS in a nutshell is really using predictability for reality check. I often go to talks that people talk about fitting. Cross-validation is one thing, but usually there's not enough attention paid to say that actually your model capture the essential structure of the data. It's good to do cross-validation, but cross-validation can be misleading. Test set is also good, but it's not often not always done when you do p-value. And stability is really looking at every step in this data science lifecycle and shake it and make sure it doesn't break, right? This circle, basically you're making human judgment calls. And you want to make sure your conclusion is not the artifact of particular human judgment call driven perturbation or otherwise. And the stability principle is very broad and flexible. You define the perturbation, you make an argument why it's a reason perturbation. You basically want to say that the data, the process could just happen the other way. And I want to make sure that didn't drive my conclusion. And you define a target of interest and then also a stability measure to say that this is the right measure to measure. If I perturb the process this way, the conclusion, if within this threshold, then I'm okay. Otherwise, it's a concern. Oh, that's what I already talked about. So if you look at the perturbation at the modeling stage, which we're most familiar with, that's where I started too. Under the IID, independent identical distributed assumption, we already have at least 3 forms, right? Cross-validation, you make it into, say, 5 tenfolds. You can do bootstrap, you can do subsampling. You can also add noise to data. You can also take the residual and bootstrap, and you can do block bootstrap of time series. So there are many versions. We often just, even the top 3, we do 1, we don't do all 3. Do you get the same result? And the newer form of data perturbation include, like as I said, in the PIAAC data, right? Do you do audio, video? If you do audio, do you get a different conclusion if you do video? And synthetic, that is PCS frame we try to build, we built, really want to incorporate PDF, PDE-driven models, right? You can build your PDE model in the likelihood, say the mean function, which I did for some work with climate scientists. That's one way, but then you have to reprogram everything. Oh, you just simulate from a PDE model and put the data together with your observed data, and then you don't have to change any of your coding. So there's a lot of convenience to do it that way than put it explicit into the likelihood. And people have been using invariance. It's a form of stability. Say if some relationship hold under different conditions, then probably it's causal. So that goes back to economics in at least the 40s, right? So that's a form of stability. And differential privacy, which US implemented last year, is also a form of stability. And the most prominent reason is actually adversarial attacks to deep learning algorithms. If you look at medical imaging, people have designed this specific attacks that it can flip the diagnosis, which is very disconcerting. And this is extreme form of perturbation. But all of that can be all unified under data perturbation, depends on the purpose. And data cleaning is really a form of data perturbation that I later recognized. When I wrote my first paper, I was not thinking about data cleaning. So here's a very famous example of importance of data cleaning. So about 10 years ago, two Harvard economists, Reinhardt and Rogoff, wrote a paper called Growth in a Time of Debt. So the conclusion was that so the data they use are different years, different countries. So each data point is high debt to GDP ratio of a country for a year, and then a measure of growth. And then they concluded that high debt to GDP ratio is bad for growth. And this was used to support austerity policy in UK and Europe, right? If you follow the news, that since the economists today changed their views about stimulus and all that. 4 years later, a graduate student from University of Massachusetts, Amherst, Herndon, and I think his advisors, Ash and Pauline, I tried to replicate it. And they found that there was a problem with data cleaning, coding error, and probably unconventional weighting. And after those got corrected, the conclusion didn't hold. So this is a very important piece of policy-driven research that hinges on three data points from New Zealand mostly. And it's not reproducible. You can say it's data cleaning, coding, but whatever, it's not reproducible. So this is, I feel like policy, if a policy is going to build on some research, that research should be duplicated or replicated by another group independently. It's reanalyzed. Tukey was, attributed to be inventor of robust statistics, right? And then we have, in regression, Lasso and Ridge, which I'll talk to, and you have now deep learning, you have many different local minimum. I mean, of course, you fit data perfectly now seem to be in fashion, then you have many, many global minimum too. And sensitivity analysis is a form of model perturbation people do in Bayesian statistics, and researcher or team-to-team perturbation. If you look at global temperature rise, you often see plots like that. There are 9 dominant climate models, probably by 9 leading groups, and they give different global mean temperature prediction. So in like probably 60 years or 100 years from now, the prediction ranges from 1.5 degrees to 5.5 degrees. So all of these are not taken into account in traditional inference framework. That I think this is people usually a climate model, right? They simulate these PDEs and they have a different granularity for the simulation, and they take the tuning of the parameters different, and then the observational data taken into account differently. So they end up with different predictions. All of that just to say that we have to recognize this human judgment calls that we do, and we better be transparent. So that's where the documentation comes in. We have reality, we have models, which are mental constructs. When you fit a model to data, it doesn't mean that your model summarize the data in the right way or capture the right structure of the data. It's our job to really build a bridge through quantitative and qualitative narratives and document it, put on GitHub so other people can scrutinize. Otherwise, and we record judgment calls. And otherwise, we're on shaky ground. So people often ask me when I give PCS talks that how do we choose perturbation? Because you'll never finish your work. There's infinite number, almost like perturbations. So if you pledge the stability principle, then you'll be very careful choosing and argue for what are the appropriate perturbations to do. You basically want to imagine, use your data or PDE to imagine another situation which is plausible and reasonable that you want to consider. And often you probably cannot do for every step, you have 2 possibilities, you go to exponential growth. You at least you fix all the other steps, but at least perturb marginally one to have 2 choices. That becomes linear. And that will make our conclusions more reliable and mitigate the dangers of like conclusion the two economists concluded. So we also go to inference. Instead of the difference between PCS inference and traditional statistical inference, that we allow multiple approaches to the same problem. And if there's a comparable quantity of interest, say, I'm interested in knowing which genes are driving this particular disease, say this HCM, heart disease. And the different people might take different choice. Some people might use Lasso, some people might use random forest, some people might use deep learning. But often it's the ranking of the genes most relevant for experimenters. So we can look at all these different rankings. And if they fit the data equally well through prediction, then maybe we should either take the intersection or look at all of them, right? So you cannot just say, oh, I have studied Lasso for all my career, I only look at Lasso. That's just not trustworthy anymore, because before we don't have the ability to code up, but now software is variable. You should even try comparative approaches and compare. So we put the prediction screening as a diagnosis, which kind of there in class of statistics in regression, but now people just don't, they directly go to p-value. So we do some screening to make sure you capture something, their signal, and then you allow different approaches and just have a perturbation interval instead of a confidence interval. So it's transparent, it's pretty algorithmic. And if you have a perfect probabilistic model, you're doing bootstrap, this is basically a bootstrap version of confidence interval. So we can say that the climate scientists already practicing PCS inference by showing plots like this. Any questions before I move to the next part?
I have a comment or question. What is the difference between stability and generalizability? Generalizability being, the linchpin of a statistical inference. It connects to sampling, survey design, and the representativeness, internal validity issues. So over 150 years of work on these things in terms of what is a sample and what can be inferred about it, is it generalizable, that has developed within statistics and econometrics. What are the distinctions?
So I would say that when all your probabilistic models are valid, then stability become, I would say the classical framework is a special case of stability.
So yeah, go ahead.
But like data cleaning, for example, is not included in that framework.
That's correct. The idea of the sample being representative of the population or object about which one wants to draw inferences is always implicit. I mean, you have selection, we have missing data, measurement error, all of that, and how one deals with them is all about making the sample truly representative of a population. So that's internal validity issues.
Yeah, but the way it's practiced, people just make the assumption. They don't even look at the data to say it's represent. They don't even say what's exactly the population. I mean, sampling survey, I think you have a very well-defined physical, like you control the random mechanism. But beyond sampling survey or randomized trials, the randomness is just imagined by the data scientist.
No, that I agree with.
Yeah.
In a way, I'm being facetious. I'm being critical of data.
No,
science.
please do.
Data science is kind of, I guess, is being viewed with some suspicion because it's beginning to rediscover things that had been well traveled in the statistics in these regards. So I don't disagree with your point that the data scientists are not
but even statisticians, when they practice their own trade, I think most people, a lot of statisticians take the data, which is not from sampling survey or randomized trial. They just start assuming X1 for Xn, like with some probability assumptions. If people are a lot more careful, then address those points, then probably we only have to deal with now, the data cleaning stage and the linguistic aspect of it. But the practice is that very rarely the practice of statistics, even by statisticians, address this connection with reality. So this is to try to make how people think through those issues.
Well,
and make documentation.
I'm very supportive of this. In a way, I'm questioning whether the new lingo, some of the terminology helps, because there is a tradition of dealing with these issues, but with many different terms.
Well, I just felt like if you think of the statistics, it's a term used for hundreds of years, like at least 100 years. And most people, when you ask them statistics, they think about t-test, they think about z-test. They don't think about these issues about population, all of that. That's the problem. So that's why I felt like we need new, more explicit terminologies and simplify things.
I'm supportive.
Yeah. So I was trained in statistics, so
I realize.
Yeah. So maybe, but I do see your point that even my former advisors will tell me that statistics have dealt with everything. This is, you can say, is a modern statistics, and taking some old ideas, you might be right at giving a little new names. But for me, it's like, if it gets young people's attention, get them into good practice, I'm fine with it, and that's what I'm doing it for. I mean, the reputation of statistics, people tend to think we only do the classical statistics happened 100 years ago. It's very unfortunate. I agree with you completely that I'm doing modern statistics, but I just feel like I will have a better reception putting under the umbrella of data science.
I think you're right about that.
Yeah, it's pretty unfortunate. It was not my choice, but the last 5-10 years, I start embracing new terms because I just get people's attention, right? I talk to my own kids. You talk to them about AI, nobody come home running, telling me about something statistic. They will tell me about, oh, I'm doing AI, right? It's just reality.
Yeah, I understand.
So I hope you see where I come from.
Absolutely, absolutely.
Thank you for the question. I definitely see where you come from too. But I feel like I made a choice.
Can I also ask a question?
Sure.
I was going to leave it to the end, but you asked for a question. So I really like your PCS and the way you describe it. It's very similar in a way to the way I think about it within informatics. But one thing comes to mind when you talk about stability is that there is no true model out there. And if it's there, we won't really find it. Or if we found, we won't really know. And basically all problems when you think about data and informations are fundamentally underdetermined unless, as you said, we use some soft information, which means what decision function, how do we clean it, how do we do this, what model do we use. So the stability is also still seems to me it's the right approach, but it still seems to me a bit flexible because it all will depend on the exact model that I will choose at the end to work, which include the data as part of it. The rest will be the decision function, the way I present the data, the way I construct it, and so on and so on.
Yes, it's stability, I think, is very fundamental, and I'm trying to build a framework. It's give some railing guide, but not dictate exactly how to do it. It's more conceptual, more saying that these are the issues you should consider. And here's some high-level principle guidelines for you to think about it. But then you do the work and you make a record of it. And there's no panacea. And the key here is to form a good habit of standardization. And that I will hope one day will become accepted as something called PCS compliant, right? So basically you have checked all the boxes. And we recently did some work with ER doctors to re-examine something called a P-scan. It's a decision rule ER doctor use to decide whether a child should have a CT scan coming in for abdominal pain. So there's this existing rule based on some data. So we use the PCS framework basically to reanalyze it and reconfirm. Actually, it's a pretty good rule. We couldn't beat it very much. So we call stress test. So we use the PCS to stress test this decision rule that we're publishing or writing up the paper with the original inventors of PSCAN, but we do have external data. We had another set of data. We reanalyze data, we also evaluate it with a new set of data, which is a smaller study. So PCS is both for you, hopefully find useful to do your own work, and also you can think about these issues for exam or critique other people's work. The reason I want to go to this predictability and stability and computability is computability I have to accept, right? Except the simulation bit, I think needs some work. It's like I'm hoping that really high level decision makers like CEOs or they can also understand predictability and stability. So even they cannot do deep learning, but they can ask questions which is connected to reality, right? They can say that, how did you clean the data? So I'm also trying to build a set of language which is very accessible to people who are not even data scientists, that they can embrace. And then we can go to layer by layer. The way statistics textbook often written, we get to the details and mathematical notations very, very quickly. And people who are not trained in mathematics tend to feel that intimidating and don't engage. And then they leave us too much freedom. I want people to come in and basically critique us, but you have to open up the process for them to come in and ask questions, right? Because if you quickly go to X1 and X and Y, then they just get lost and they just say, oh, okay, you do it. But we don't really have that power to take a problem away and come out with something I personally feel comfortable. You need domain and other people to work with us. And then you have to create this language and these concepts. Other people, we can overlap with other people's understanding, common sense and things like that. I joke about that one day I might be killed by my own algorithm because I have, my group have software on the internet. We have no label, we have nothing on the algorithm. Somebody can take it and start treating me, right? There's nothing. We have, before algorithm, it's only for your collaborator, it's a cottage industry. Now it's a product. And with open source, which is great, but there's a downside that they're not always vetted with the right labels. Medicines have labels, so certain people shouldn't take it. We don't have any label saying that certain problem, this algorithm shouldn't be applied. And I think the first theorem in statistics or in machine learning, any data work is nothing works all the time. But we don't tell the users why it doesn't work. We often don't even know ourselves why it doesn't work. If you look at all the publications, all selective, it's all the cases when it works. And people the student, the beginner is going to have an illusion that anything will work. You do a regression, we assume Gaussian model. Therefore, all data has to satisfy the Gaussian model. Because we don't really spend enough time critiquing and show them things go wrong. And I think we're writing a textbook based on PCS, try to put more emphasis on the other things. Good apply, data scientists, statistics, machine learning all know, but not really widely like.
Your conclusion is very good. I'm a little concerned that you left out the value of theory. And you even pointed out yourself that data can be poisoned. With theory, you can have an alternative check on the data. Plus, there are many examples, far too many to recount, where theory made predictions about reality, but it took decades before that data evidence was brought to the fore. The Higgs boson, for example.
Well, I was trained mathematically, so that's why we're kind of coming back to do some PCS theory. For me, the way I approach theory is now actually I want to see empirical evidence before I analyze and under multiple sterilized models. So definitely there are numerous examples that theory did good prediction. There are equally even more examples theories didn't work, or people just work on the theory which is not relevant to practice. So you know, simulation, that's where the computability, that's where you have to do a generative model, but your model has to be taking into account the particular domain, you know, knowledge to design something. And we, for example, first, we now just finished a work to prove some model selection consistency of some derivative or like output of random forest with a supposedly a Boolean model, which we think is relevant in biology for biomolecular interactions. And we proved, you know, if you take the random forest, take the right output, then can be model selection consistent. So I definitely, we're going there, but I like to build more conceptual framework first before we go to the theory part. That's, I mean, when I was younger, I took theory first and then, you know, but now I'm doing the other way because it's just, a lot of the models people study in theory are not really capturing the reality that a lot of the problems facing anymore. Because people often say that, oh, we have guarantees under theory if the condition are more or less okay. But if the conditions cannot have any empirical support, the guarantee in theory doesn't say anything about practice.
I don't think there's any theory in guarantee. There's no guarantee. Yeah. I agree.
Yeah. So I love relevant theory, but a lot of time relevant theory is very, very hard to do. And I also more for the really people with a lot of experience. And then I think that most of us, the theory we do, if we don't have empirical evidence, are not a genius streak. I mean, if people have a genius streak or something, I'm all for the top 5, 10% of the people to do theory, I have no problem. The problem is we have a lot of mediocre theory. So I make my choice, not doing more empirical work. But I have nothing against theory. We're coming back my group to theory.
Good answer.
I suggest that we continue the second part of Bing's talk, and then we leave more further time for questions at the end.
Okay, so let me do this. So this is a joint work with Gallant Lab, my collaborator for 15 years. And the project was actually led by my group. This paper is still being written after some years. We're still writing it because Jack has very, very high standard and for writing. So Reza is now a faculty at UCSF, and Yuan is at Duke. And Adam was a former student now at Google, and Mike was a former student, Jack, and Ben Wilmer was a postdoc 10, 12 years ago, collected data. It took Ben, who is now at Oxford. It took him 2 years. So it's very expensive data in terms of human time. So this is, I've heard of deep learning from the first talk. And what I will concentrate on is this area of visual cortex called V4. So there are 2 pathways for visual information to be transmitted to our executive center to make decisions. One is what, one is where. So I'm looking at the what pathway, V1, V2, and V4. V1 is more like edge detector, location selectivity, all of that happening in V1. Sometimes local processing get useful features. And it's like can characterize pretty well with a Gabor filter, Gabor filters. And then V2 is kind of similar. V4 is a very, very difficult, elusive area that has been for decades. We still don't have a very clear picture of what's going on. And then on the other hand, the last 10 years, deep learning is really creating all the waves about computer vision advances and self-driving cars, which now I think people realize it's not as easy as people thought 5 years ago. So let's go back and look at V1. So V1, how V1 was understood. And there were 2 guys who, Wiesel and Hubble, got Nobel Prize for their work in the late 50s. And what they have, what you're going to hear is the neuron firing rate. And this, what you see on the screen is what this cat was seeing on the screen. So what you hear is the firing rate. And now you're inducing firing. So this is proof that this neuron cares about this location. I hope we all agree. So put some stimulus there, it happens. So this is a proof of local selectivity. So traditional physiology to characterize neuron by what excites the neuron, you hear a lot of firing. So to understand V4, they use the same idea, just try to figure out what are the complex shapes and patterns excite V4 neurons, which is a higher visual cortex area. So they design very artistic and shapes. And you can see the darker the shape, the more excited neuron is. So, but you have Cartesian, you have polar, you have parabolic. But what if things we haven't thought of and the neuron care about, right? So with all these synthetic stimuli, you might not cover. And people also have this very elaborate design of different curvatures, right? Concave, convex, all of that, and to see which neuron care about what. So Jack, when I started working with him like 15 years ago, he was a pioneer at the time. Now it's more or less accepted that you should use natural stimuli to understand our visual cortex instead of these very synthetic ones. At the time, we had a black and white database called Coral, I think, and then randomly selected images, and then the neuron firing rate was recorded. So about now 10 years ago, two of my best people, Julien Merel, now back in France as Neuron computer vision lead in Grenoble, and Yuval Benjamini back to Israel Hebrew University, was the applied student, and Julien was a computer vision guy. So we had two of my best people try to work on that. So we built a 2-layer neural network based on computer vision, like type of the sift. So it was pretty transparent. We used sparse coding, and then we had added a direction, and we used sparse coding again. I had a state-of-the-art performance. So what I mean by state-of-the-art predictive performance, we have a test set aside with 10 replicates, so it's a high signal-to-noise ratio. And we set the bar as if we can reach, we have a population 71 neurons, they're not simultaneously recorded, right? So this is one at a time. And if we can achieve the predictive performance measured by correlation, that's what physicists, physiology does, because you can never match the magnitude, to the V2, which is an easier region, then we call a success. So that's what we matched. That was, the data was collected quite a few years earlier than that, but nobody can really do good prediction. And then DeCarlos at MIT they're more interested in like IT, and they have these semi-natural images. They have an object on impulse on. So we can be on this parallel, working on similar problems. And they had, they beat us to it in terms of predictive performance. And we have been concentrating on interpretation and understanding. So the question to ask is, can we characterize these neurons and in an image form, and maybe we can replace the handmade, like complex shapes, have data-driven design to feedback to be proven that a neuron care about a particular shape. And then deep learning happened. So I gave a talk 5-6 years ago, and Benji was talking after me, and he was doing deep learning already. And I had my own 2-layer neural network, and we decided, like, let's try deep learning, see what happens. So what I end up doing in a nutshell is like we end up using ImageNet trained AlexNet, say, and then use the first few layers as a feature extraction. Just feed our black and white images right into this already fitted deep learning network, first few, and use it as feature extraction. And then we use regression with the response as the average neuron firing rate. And then this did better than our own homemade neural network 2 layers. And that's why we start working on deep learning. And then we end up with 18 different models, take different versions of deep learning and regression, lasso, or ridge. And then we were stuck, but why? What do we do with it? Because you end up with different images, and we end up using stability principle again to get what we call consensus images that can be fed back into the closed loop experiment. I was amazed because that's why I jumped into deep learning. Usually I try to stay away from the hot area, but I thought this is something there. I have 2 of my best people work for 2 years, and I just take the feature extraction from ImageNet and then linear regression. And it worked in terms of prediction performance. It beat our own self-made 2-layer neural network a tiny bit better. but it's just basically painless, right? You have the feature extraction, you do linear regression. So that's what we did. So we took a trained CNN by other people, AlexNet, and then we just use the first 2 layers as feature extraction, and we just make 3 channels, black and white. We only have one like grid, right? So we just made the 3 channels and make it colored, and then just fit it in, and then we did the linear regression with the response as a average firing rate over small intervals. So this is in 3 levels transfer learning. We have black and white and trained on color image, and ImageNet human data. And here we have small behaving macaque. And then ImageNet was trained on high level classification tasks. And we're now going to the neuron level, very different scale. So one possible explanation is that the first few layers of all this deep learning are really pretty good approximation to early visual cortex processing. So then we, of course, fit the weights of the regression using neuron responses. That was quite surprising to me because, but this used small data. We had very limited data, right? Even we have our own hand, but some people still like our early work better because it's more transparent, more interpretable than this. It's harder to understand. That's why we also develop kind of interpretation methods. You can see that this is different layers of AlexNet. And then the Gabor is the control model. Definitely we do better in terms of prediction. This is average prediction accuracy over 71 V4 neurons. And not just layer 2. In the beginning, we're hoping that, oh, V4 just map nicely into, no, it doesn't. Layer 3 and 4 all work pretty similarly. And if you follow the physiology thinking, right? If you have real neuron, you want to see what images excite a neuron. So now we have a model. Let's use the model to find what images excite this model neuron we call DeepTune, inspired by Deep Dream, which is for features. And you can see start with white and you end up with this curvature looking image. And then we can also remove many nodes, compress, and we also see this curvature. You said this is an artifact of your model. Some actually are artifacts of the model. And then we went back to the original black-white image in our database and look at the model. What are the images make the model responses large? And you can see that they all see this curvature, kind of this direction. And then you said, this is just artifact your model. This is fair. So we went back to the average test data with no model fitted and see what are the ones give high responses. This is the black and white. You also see curvature. So this is a proof that the curvature, the curve image we got out from a DeepTune is not the illusion. It captures some reality. And the different colored curves are different models from different versions of deep learning, all give very similar prediction. To expand on that, here I show you 3. You have red, AlexNet plus Lasso, blue, VGG plus Lasso, green, GoogleNet plus Lasso. So they all very similar. And they all miss a little the high peak. It's also because we use like 1 or 2. We don't have 10 replicates. So the training data is just a lot noisier. So we cannot really have that sharpness, which this test data has. So quickly we end up with 18 models, right? You have 3 different deep learning. Each you take different 3 layers. You have 9 times 2, because Lasso or Ridge, you add 18 models. So if you maximize your 18 models, that's the DeepTune images. They all have this kind of curve with certain shape, certain angle appearing, but they're not the same. So it's only looking at the together, you're going to believe this curve, right? You see, look at GoogleNet, because it has small convolution filter, then you have this weird, like eye-like things. And this periodic kind of curve is really artifact of the convolution, but the curve is there. So we want to consolidate to one consensus DeepTune image. We again went to the stability principle. So for this 18 images. Each of them, you have a model, and we regularize a bit to get some smoothness. Then you have 18 different surfaces. You do gradient ascent, not descent, because you try to maximize to see what would make this neuron fire. What we did, we went to the gradient level. We have 18 different gradients at any point, which is an image of the optimization. Then you take the lowest gradient, and then you walk in that direction. And that's what we got. And this is 10 different initializations. You get something very similar. So then we have a representation for each neuron, the preferred image, and then we can cluster them. So to understand this population, 71 neurons. So you see that there's this curve, as I showed you, people already figured out the VIII neuron care about the curve, but it's a lot more complex than what humanly designed, very neat, artistic looking shapes. And the outlier is really like a VIII neuron. It's higher, bigger receptive field. But if you look at the cluster, they don't cluster very well. This is hierarchical clustering, which is cut it somewhere. So you have this artificial, like the cluster, but actually it's pretty much connected. It just shows the diversity of complexity of the shapes that patterns VIII neuron might prefer, right? Some artifacts are model, some are not. But the key is, this has become like our scientific recommendation system. This is suggested images you can feed back to the electrode to prove that certain neurons care about certain patterns. And the DeCarlos group actually published a paper, they were kind of on the parallel line. Jack doesn't do physiology anymore, so we didn't go back to the experiment. And we want to crop, if we do it, we want to crop the images. We don't want to take the whole, because some artifacts want to take more local images and then maybe combine them and use as a resource to come up with the design of images instead of the artificial, like synthetic ones designed by humans. So I want to just say a little bit, it's really a shout out for our pipeline we developed called the constructed decomposition to interpret in deep learning models. And this is a series of conference papers, ICLR and also ICML. So the first one proposed the contextual decomposition that compared with other interpretation methods for image, we also give important not just one pixel, we also give groups of pixels. And the second paper really used the scores to build a hierarchical interpretation. And the third one used the scores to de-emphasize something we don't want the algorithm to learn. So it's kind of feedback. Use interpretation saying, this is, you don't want gender to be a factor. So you de-emphasize in the training the reliance of your classification on gender. So this is just a very quick example that this is a prediction for PIAAC. And then we basically highlight the places that are important for predicting there's a PIAAC in the image. And you can see quickly skates become a good predictor for PIAAC, because even you remove the PIAAC, you can still predict because they are kind of highly correlated. And we worked with cosmologists to use this. I usually like, this was developed more generic methodology. I really want to put into context. So we work with a group of cosmologists at Berkeley. Now Francois went back to France. That they simulate this origin of universe. This omega m is one of the important parameters. They have simulation, forward simulation, and supposedly we observe this on the purple image. And can we infer omega m from what we observe today? Right, so this is simulation data. And we're able to really, they use deep learning to do the inverse of omega m. And we're able to really interpret things, go to the transport domain, Fourier domain, that's the meaningful one to show that the certain frequency very important for estimation of omega m and other frequency not important, which agree with what they believe. So we actually now generalize the CD to a transformer domain and also building on wavelets. We had another success story with some molecular biology imaging problem that we want to see two molecules, one kind of trigger the other. And we also want to use deep learning to predict. And then that worked out pretty well because we have a lot of human extracted features. And this is a general paper we wrote, try to kind of put together some definition for interpretable machine learning. And we have something we call the PDR, that's Terra. You want an audience, when you talk about interpretation, you want the predicted accuracy to make sure you have reality check, and you want also distributed accuracy for relative to the relevance of the problem. So this is more like just putting a plug for interpretability paper. Some people call explainable AI. And just to summarize, I hope give you a very quick overview of our PCS framework, and documentation is hugely important. There's no magic here. You just have to record. And I think writing something out make us think clearly. And because you're putting things out there, you're just more careful. It's just human nature. And at some point, maybe you have all these documents on a Zoom, and we can have graduate students to random select some and read and critique. And that will also make people just self-discipline and do more rigorous job in their data analysis. And show to the DeepTune. And then I had a very, very quick run of our interpretable machine learning works. And I hope you find PCS useful. As brought up already, I think much theoretical work is needed for PCS. We did very simple analysis in a genetic bound. So it's a simple linear model. We can show there that basically the PCS inference is really testing a more fattened non-hypothesis, more robust hypothesis testing. This is all under traditional statistical assumptions, and we do the PCS procedure and analyze it. So definitely hope more people will join us. And domain knowledge is hugely important. And we also try to use PCS as a framework for general recommendation. We have done other successful case study PCS, which in genomics, in particular precision medicine and drug discovery. So I'm more confident now that it's a useful framework. And we're finishing a textbook, which we have signed a contract with MIT Press. So this summer, we shall have an online interactive free version. MIT is really nice to agree to a free online version, and the paper version probably won't come out until next year. And use this framework and really take care of the whole data science. Like we have a chapter on data cleaning, on computing platform, and inference and predictability, all of that. So, and the last is the shout out for all the data science work we're doing at Berkeley. We have a new division. We hope to become a college with our new leader, Jennifer Chase. Many faculty, including myself, worked very hard for 6 years before she came. And we have data 8, data 100, data 102 jointly designed and taught by CS and staff faculty. Thank you. So these are the papers.
Thank you, Ben.
Thank
Well, Min, go ahead.
Thank you very much. And I think that the first thing we probably let's show our appreciation in perhaps in a Zoom way, and by using emoji, if with a putting a thumb up or things and clap your hands, and in whichever way you feel appropriate. And unfortunately, and we probably not wise to get everyone switch the microphone on and clap their hand. But thank you, really, thank you very much. Very exciting talk, and very, very timely. And we are a little bit short of time, and we actually a little bit overrun. So I just have time for one question. And since Armin has raised his hand, Armin, please. You're muted.
Very impressive talk and presentation.
Thank you.
Impressive in terms of covering so many things, within.
Maybe too much.
It was amazing. But one thing is that many economists feel that there's not much economics in machine learning, and I think one of the reasons is that. Of course, one part of the machine learning is the prediction. So I think there they love it because everybody is using right and left and doing the forecasting, and so machine learning is doing a great job in doing predictions and all that. But the things in which the economists have a great interest is what is called marginal effect, the derivative of the predictive model. But that, for example, random forest, you can have predictions, but you cannot have derivatives simply because this is a weighted sum of some response variables, and the weights are just discrete functions, and that you cannot differentiate and so on. But then somebody told me that the deep learning models, they can be used to have predictive models which can have derivatives. And the graph I see from your some of the predictive models looks very smooth and all that. So is that true? I mean, the deep learning can resolve that issue of getting the derivative of the predictive models? I mean, that's what the...
Well, I mean, deep learning does, I mean, it's a very smooth model, so you can definitely do derivatives. And random forest, I think you can probably smooth it and get derivative that way. So we haven't done that, but people usually do derivative deep learning model to get some saliency map, but it's very local. And for random forest, we did something called iterative random forest. We add stability, and we went for nonlinear model selection, and was very successful for some Drosophila problem. And that's what the building block we're doing for cardiology. It's adding stability, because one problem is random forest, the path. So it's not our idea, other people already thought about it, that if two features fall on the same path of a decision tree in the random forest, then they probably interact nonlinearly. But it's very unstable. Same thing as I mentioned with Lasso. So we added stability. We have something called iterative random forest, and we can find relatively stable interactions. And for Drosophila enhancer prediction problem, we got really good result for pairwise interactions. 80% of what we found already become, people already validated in physical experiments before we came. And we're building on that. And now we're finding it, we have to add some other things, because what happened with cardiology, with Drosophila, it's all purebred, right? It's a lab, flies. So they're very similar genetically. But when you go to human disease, human common traits, the signal is very weak. So I've been struggling right now to do the cardiology. We validated the pipeline for something easier, red hair, with UK Biobank data. Red hair is very genetic, and we can show that our pipeline works, right? We have to add more bells and whistles on top of it to random forest, but it's a very key non-linear model selection technique that we're looking for thresholding behavior, which is really valid in biology, because you need the abundance of biomolecules to interact, right? So there's biology reasons that at that genomic level, thresholding decision tree is a good match with the biology. It's not all interaction, but some interaction do happen that way. So deep learning, we haven't tried yet. I just wrote a proposal saying that, try deep learning, but we will get there. And I want to connect the two.
Yeah, look forward to it. Thank you very much.
Thank you.
Thank you for the question.
I think that we running out of time, and I think Amos is waiting to close the conference, and I myself have a lot of questions. Most of you have probably a lot of questions, but what I strongly recommend is go to Bingru's webpage, and there's a lot of paper, and really you will enjoy reading them. And I've been reading them, and so excellent. Let me thank the speaker again, and I'll pass back to Amos.
Thank you. Thank you very much.